Morning, y'all. Listen, guys, we have an exam next Friday, and I intend that we will move into Chapter 6 before that exam. We can maybe even finish Chapter 6. So we'll just sort of wait till next week and see how we come along. But part of Chapter 6 we're going to do via screencast. I think we've done that before, right? Like where I send y'all the clips to watch. Okay, well, I'll send it to you. Oh, did I send you an email already?
6 and 57 of chapter 6, the reflection and refraction.
Okay, so I already told you that chapter 6 was going to be another exam?
Yeah.
Okay, yeah.
Wait, so you felt kind of insulted that we didn't tell you since we didn't...
decided to take it off.
Chapter 6 is easy though, so I think it'll be good for y'all to have it on there, so it'll be some easy problems. Alright, but this is easy too, right? This chapter 5 business?
It's something we've already gone over. We've already done vectors like this.
Yeah, we've done.
It's just
talk
going to be a
about it
pain in
and
the
stuff.
butt to figure out, like, look, oh, it's going to be that way just because this is into the page, this is out of the page.
Right. I think we'll probably skip a couple things too, so we'll make. What's that? What?
Before we start,
Can you go over now?
193 again, like just in the note direction and stuff like that. And then the out of page and the vectors, where they go and all that stuff.
Yeah. The symbols that we use, you mean?
Yeah, that's the part I'm trying to figure out.
Does it actually work?
The top of 193.
This business right here? Okay. We're gonna. You mean like how to use the right hand rule?
Yeah, I mean, it just shows like, okay, so you show that symbol, the circle, with the dot at the center shows that it's coming out of the page.
Right.
So if you were to set that up as your right hand rule, I mean, that would show it coming out of the page. It's coming out of the page like this to me.
Right.
But then it's just the vector going the opposite way. So to come out of the page and have the vector going that way, it would have to come this way with the vector going up, not down.
Can we do some other examples? Is that okay? Yeah. Have we started the concept test for this?
No.
Okay, let's do these because there's a series of questions here. Is that okay?
Wait.
Well, that will answer.
Can we just review the rule again because I just forgot?
Yeah, I'll do it right here. All right, so I'll help you with this first one, okay? Let me get my clicker started first, but I'll give you the answer for this first one. You just forgot just now?
Yeah, like, he already passed 2 days since that.
Oh, right.
Just because it passed a whole day already.
I read this book recently and it was about learning, but about, our short-term versus our long-term memory. And most of the times when we take exams, we store stuff in our short-term memory, right? And then we sort of dump it right afterwards. And then it's sort of accessible, but not really to us. But the problem with short-term memory is that, what's that? Yeah. But the problem with short-term memory is that it doesn't hold very much. Like you don't have a lot of RAM, basically.
You just used another word that I don't think many people.
Right, like in your computer,
access memory.
or your computer has this place for short-term memory where it like puts information while it's doing calculations, and then it has your hard drive, which is really
copy
big.
and paste would be a consideration.
It
Stores that information that this is considered copied, and whenever you do something else, it gets rid of it the second you turn off your computer.
So the key is to get stuff in the long-term memory. All right, so right-hand rule. A couple different ways you can do this. Did I tell you about my new sign? Yeah. So you can do it like this.
Hey.
Let your finger go in V.
Okay.
V is into the page, so your index finger goes into the page, and then your thumb gives the force. So in this case, the force would be to the left.
Okay, so you're saying that the index finger, the middle finger, and all those have certain...
Right, they have, if you want, you could write V on this finger, V on this finger, and F on this finger. This is also called the palm rule, the right-hand rule, in contrast to the curl rule, which we'll do later. And the palm rule, it works a little bit differently, but the same idea. That V goes in this direction, your finger's in the direction of V, and then the magnetic field comes out of your palm. So the palm would go into the page, as opposed to coming out of the page like this.
Alright, that's the part that was throwing me off, because, so certain fingers are certain.
Right.
So B is your palm, or,
Right. B is your palm.
or it's the middle finger.
Or the, yeah, the middle finger. Yeah.
And then B is your index, and then worst is your thumb.
Right. Right. So E is the right answer for this one. This seems kind of ridiculous, but it's not really. It's useful for you to think in 3 dimensions like this. There's a draftsman, our former draftsman in my other class, and he said that they actually do this a lot, like when they're dealing with 3-dimensional vectors, 3-dimensional drawings and what have you.
Use the curls, you know, like for torque, the bending.
Oh, right.
And stuff like that.
Mhm.
You know, which way clockwise or whatever. That's what.
All right, just a few more seconds. Hey, good job. Why should you never trust an atom? They make up everything.
Oh.
An 8-year-old told me that too.
I was on the billboard by like a little window repair shop at Enterprise.
Oh yeah. All right, so try it on this one. V is to the right.
Sounds like chemistry here.
Q is into the page, or V is into the page. What's the direction of the force?
Sounds like a chemistry joke. How fun do I make chemistry jokes? Pretty happy.
All right, stop at say 50 seconds. 5 more seconds. Just guess if you don't know. All right, so V is to the right. The magnetic field is into the page. It'll be like this. So your thumb points up.
No, it's fine.
Yeah, you have to use your right hand. Yeah. Oh, the palm rule is the same, Lindsay? No, the palm rule would be the same. Let me show you. So you would let your fingers go in the direction of V, and then the magnetic field would come out of your palm. Right, the previous one, the magnetic field went into the page. It had X's, not dots. It's going in the negative Z direction. Right, the magnetic field goes in that direction. Does that answer your question? Okay, you sure? And it's correct? Okay. Okay. All right.
So either way, you're going into whatever this direction is.
Whatever the direction of the magnetic field.
No, I mean like, this is going in like from this side to this side. That's how it goes, right?
Imagine the magnetic field comes out of your palm. And so the magnetic field's into the page, your palm points towards the page. If the magnetic field is out of the page, it points like this. See, it's saying here, magnetic field is the direction of your middle finger right here.
I'm just gonna stick with your fingers.
That's fine.
Yeah.
You just check that one thing. Yeah, it was into the page on this one. It's goofy, isn't it? All right. Here, the direction of the magnetic force.
Do we talk about that?
Where here, your magnetic field is to the right. So your palm is going to look like this, or your palm will be pointed in. The magnetic field is in this direction.
We're going to be like Okay, pretty much the answer is this, everybody.
Slicker.
Oh, look, that's interesting. When you want to use it, it's just doesn't look at the person and.
So V is up, and then you have to move like this to have your palm push in that direction.
We have to stand up to do this.
Or if you're doing your fingers like this, V, your index is up, and your ring finger has to point in the direction of B. All right, just a few more seconds. 1:15, I'll stop. Is this answering your question, Rob?
Yeah,
Yeah.
yeah. Right, then the part that threw me off was the fingers having to be in exactly like a certain.
All right, how about this one? Hey, Lauren. Remember our expression for this? F equals QVB, and the definition of a cross product is VB sine theta. Here our V and B are parallel with one another. Remember what happened with torques when R and F were parallel with one another?
I wonder what people would think if they record just this class. With no audio and just doing this randomly.
Right. It's like some
Watch.
priestly activity.
Watch, yes, these people attempt to let it slide like with one hand signal.
Did you also use this just like to check yourself? Did you use the JK method?
These weird hands on.
Yeah. Yeah, I suppose so. So you would say that,
So right here,
okay, well, that's the answer. So just a few more seconds, 123, let's say, or 125. Let's see. That 0 is right.
so with this one here would be like a JJ. So
It would be J cross J. Yeah, if you wanted to do the IJK, you would just say, well, this is in the J direction, and this is in the J direction. J cross J is equal to 0. All right? Or like, for example, on this previous one, you could say B is in the I direction, V is in the J direction, and so J cross I equals negative K. If you want to do that, that's fine. That might work
Just
actually.
a double check. Kind of a
Yeah.
sandwich.
So it was 0 because V and go in the same direction.
Theta equals 0 degrees, right? So these are not orthogonal vectors, so they do not produce a force. It's the same with torque. If you remember, if R was along the same direction as F, right, it's like opening the door by pushing on the door jamb, right? You don't get any torque. A beam of atoms enters a magnetic field region. Which path will the atoms follow? I should have saved my atom joke for this slide, huh? Think about atoms and what they are.
So what's the name of the thing for again? How are you?
Magnetic field. Don't think too hard about this one. Stop at 115. right answer here is B. Why is it B?
Because atoms are neutrally charged.
Right, atoms are neutrally charged. So they will feel here, for an atom, Q is equal to 0, so F is equal to 0. So they will follow path 2. Now, let's say, what would be the charge of the particle that follow path 3, right? So for path 3, I would have a velocity in this direction and a force in this direction, and my magnetic field is in that direction. All right, so I would say B is into the page like that, and so my force should be up. So what type of particle would feel a downward force? A negative charge, right? So negative charges would feel path 3. What about 4 and 1? These are straight line paths.
Neutral charge, shot at an angle.
Right, neutral. There is no charged particle because, as we'll see later, the magnetic force is a particular type of force that produces circular motion. You don't know what type that is? We call that, huh? What type of force produces circular motion? Centripetal, right? So it's a centripetal force. It's always perpendicular to the velocity, and so 1 and 4 are not circular paths. To get those paths, you would have to turn off the magnetic field right after the first force responded. All right, here, this is a similar question. Proton beam enters a magnetic field. What is the direction of the magnetic field? Now we know that the magnetic field, or what's the direction of the force, rather, first of all, initially. So at this point, what is the direction of the force? It's up, right. So my force is up. My velocity is initially in that direction. So I want to know what magnetic field produces that force.
Hey. Senor.
Rob, if you're using your thing where you're saying that V is in the I direction, F is in the J direction, you have to be careful because on this one, for example, it would be I cross something equals J. And you'd have to be clear on what that is. So you just need to make sure you get the order correct. Because there is a particular order. If you get the order incorrect, you get the wrong answer. All right, just a few more seconds. I'll stop at 155. That must be right.
Must be right.
Into the page, let's see, so V is in this direction, F is up, and so yeah, it's into the page. And notice that as this goes along, I can take these vectors, they're always going to have this orientation, and so as it goes along, it's going to move up like this. So the velocity vector goes up, but the force vector goes in. So that force vector is going to change, and the velocity vector will change. They'll always look like this. Right. So notice that the velocity and the force vector are always perpendicular. Right. And that is then, by definition, a centripetal force. I will see that that becomes important for the mass spectrometer, and it operates on that principle that the magnetic force is a centripetal force. Have we covered mass spectrometers yet? I think we have everything. All right.
You haven't mentioned anything, so.
Yeah. Okay, we'll come back to this. This just deals with that. Did not sleep very well last night. A little girl was getting up in the middle of the night. She didn't go to bed till like 9 o'clock. Like she was up, and like we went to bed at 8, and she comes into our room and is like, I can't go to sleep. I'm like, what about me, right? She didn't care. Most of you don't have kids. So.
I'm sure she did.
No, she did not care. She just wanted me to put her back to bed.
Mom, 8 o'clock.
At least you can put her back.
Lucky.
What's that, Catherine?
At least you can put her back to bed. It's her fault. Anything, so she can't see anything when she was here.
Oh.
She'll look back and be like, wake up. Wake up.
All right. What have we done? Oh yeah. So force is in a wire now. So magnetic. Remember, if we have a current in a wire, this is the same situation really. I have a charge moving through a wire in a magnetic field, so it's going to experience a force. How far have we gotten here? Yeah. So we can find that force by IL cross B. Here you might think that I is the vector quantity, but remember I, current, is a scalar quantity. So it's really the vector quantity here is L. And we'll work through some problems where you have to actually find what is the vector notation for L, where L is the length of the wire. If we want to find the direction of a wire, a force on a wire, it's the same as we had before. B is up, right? So the force here would be into the page. It's the same as we had before, but now instead of our finger going in the direction of B, our finger goes in the direction of I. Our middle finger goes in the direction of B, and then our force is into the page in this case. What about this next one? What is the force? Let's see. So current is down. Magnetic field is into the page. So right. Yeah, it's to the right. The force here is to the right. B is into the page. So I is to the right. B is into the page. And so our force is to the right. How about I here? It's the same, right? I is up. B is out of the page like that. It's coming toward you like an arrow. So B is to the right, or F is to the right. So see, these are the same applications of that palm rule. You're just imagining now that your charge is constrained to a wire. So a current carrying wire in a magnetic field will feel a force. And so that's the idea behind an electric motor, which we'll see in just a bit. Also the idea behind an electric generator is the reverse of an electric motor. Let's try this. Instead of thinking of this as a force, though, let's think of this as you're moving a wire with a certain velocity through a magnetic field. What is the direction of the current created in the wire? If this helps you to think about it, you might think of this, let me just make this wire bigger, that you're actually pushing on an individual charge within the wire, a proton we would imagine, pushing it through this magnetic field with a certain velocity. So what direction is it going to feel a force? Is it going to feel an upward or a downward force?
So that F is not, doesn't stand for force and applying current.
No, I meant to say V. Yeah. So you're pushing this wire with a certain velocity through the magnetic field. So you can cross out the F and write V. Does anybody else have a thing that y'all do? Y'all have a thing?
Mine is just to be excessively goofy.
So the arrow is the direction of B, right?
Of V. Yes. The velocity.
Should always bring around a set of drums and whenever someone makes a joke. Why do you keep that?
All right. Do about 10 more seconds maybe.
Keep out some bongos and a little simple.
At 140, I'll stop. Good job.
You didn't even have to tell us the answer.
I know.
Scared.
You're very proud of it.
We can also calculate this. So remember, F equals ILB sine theta. This is just based on our definition, which is IL cross B, and then the definition of a cross product. So let's just try this. Just calculate your your current that's in the wire. So this is at its S in a generator. You push a current through a magnetic field, you generate a current.
I guess we won't have something like this for like it's in opposite directions. And then sine would still be 0.
I think if y'all's name is back right, yeah. All right. 10 or 15 more seconds. Stop at 235. Yeah, that's right. This is a simple calculation, just based on this relationship between F, I, L, and B. We just say the force is 12 newtons equals the current, which I want to know. The length of the wire is 1 meter, and B is 2.4 Tesla. And then sine of 90 is 1, and I solve that for I, and I find that I is 5 amps. Now let's try this quick test question. This is very similar to what we had before. The only different part from a free particle is you have to figure out what is L in this case, because I have these wires and I have certain angles. I have to find out what is L, and then it's a matter of just doing the cross product. So here I have 2 wires. It says that each section is 1.5 meters long, and I have these angles. Theta 1 equals 45 degrees, and theta 2 is equal to 30 degrees. And I wanted to know what is the net magnetic force on the wire if the magnetic field is 2K Tesla. So 2 Tesla in the positive Z direction. All right, so you want to write L in vector notation, all right, because remember that F is equal to I, which we know the current is given, it's 3 amps, times L cross B. For this particular problem, you have to do it in 2 parts. So you have to find L for the first part, and then L for the second part. I'm just going to do it for the first part, okay? So I have this section of wire right here. and I want to write it in some vector notation. So this length of wire has a y component that is in this direction. I'll call it L1y. And then it has an x component that's in this direction, L1x. And then similarly over here, this wire has an x component, L2x, and a y component, L2y. So you can see it's a simple trig, right? To find L1y and L1x. Let me give you all a couple minutes. Try to express L in terms of its x and y components. I want to know L1 in IJ notation. And then once you find that, you can just do the cross product, crossing it with B. Bless you. Oh. All right. So here, L1 is going to be the x component in the I direction, plus the y component in the j direction. Lx, this is L1x and L1y. Lx is going to be L times the sine of 45. Let me show you where I got that. Because usually our x component is written with a cosine, right? But notice here with our triangle, this is L1, this is L1x, and this is L1y. This angle right here is 45 degrees, and the sine of 45 is opposite over hypotenuse, so that's where my L1x comes from. It's going to be L times sine of 45. Go with me on that? It could be cosine, right, because it's 45 degrees, because cosine equals sine 45. But if the angle is different, that wouldn't be the same. All right, so L sine of 45 times I plus, actually that's not right, minus L cosine 45. Why is it negative?
Negative direction.
Right, so this component of the vector right here, L1y, is in the negative j direction.
Why couldn't you bring theta 1 down to where L1x brings
Theta 1 right here, you mean?
Yeah.
Yeah, those are the same angles. Because I have two parallel lines meet. So this is my L. I have two parallel lines. So this angle is equal to this angle. Remember that from geometry, 9th grade or whatever? That has a name. There's some type of angle. Are they complementary? Okay. All right. And then I know L. Do y'all have values for this? L sine 45, L cosine 45?
1.06.
Okay, we'll call it 1.1i. minus 1.1j. So that is my L vector. I would do a similar thing for L2, right? Now let's try the cross product. So I want to know the force, and now we're just doing the first part of the force. F1 is going to equal I L1 cross B. This is a pretty simple cross product because B just has one component, but I'll leave you for that to do it. Lots of vectors in this chapter. I'm going to go ahead and start writing in the answer here. What is I cross K equal to? It's some sort of J, yeah, so I, J, K. You can use your right hand rule. I cross K is negative J. So that's 3 times negative 2.2J. And then J cross K is positive I minus 2.2I. And so the answer for F1 is minus 6.6I minus 6.6J. I reordered them there just to be in IJ order. Alright. Now, on this problem, you would go through the next step, which would be to find F2. So you'd have to repeat all of this. This is kind of a long problem. I probably wouldn't make it this long on a test. But you would go through and find F2. Or, excuse me. First, you'd have to find the components of L2. That's equal to, LX2I plus LY2J, just like we did before, finding the X and Y components. And then you would do the cross product, I, L2 cross B. And then when you found the X and Y components of F2, whatever they are, you would just add it to F1. So the net force would just equal F1 plus F2. I wouldn't make it that long for your test. That would be too long. I don't know what I was thinking. But it's just repeating the entire first part. No, this is a, when I say quick test, it's like, this is a question from a previous exam. Yeah, Chris?
Back at the top, you got the 1.1 I minus 1.1 J.
Right.
You got that from L sine 45.
Right.
What is L?
L is the length of the wire, so it's 1.5 meters. So, I'm sorry I didn't write that out explicitly. 1.5 meters times sine of 45, that's equal to 1.1. See, this,
1.06.
yeah, 1.06.
Yeah, 1.0606. Unless your thing's in radians.
Yeah, unless you're in radians.
Name and reading.
Okay. Yeah, for this class, you'll always be in degrees. So. I know, because in calculus, you'll need to be in radians, right? Be careful with that.
Yeah.
It took me a while to figure out how to get to reading. I gotta figure out
I remember when I was an undergrad, like I had a special note at the top of my calculator that said check radian mode for every test because I had to switch back and forth between calculus and physics or
I
whatever.
carry around separate calculators. I better shoot this one on radians and this one on.
That's a good idea. Just carry 2 calculators. What's that, Catherine?
This one's up.
Can you go back up again?
Yeah.
Just want to see the last part.
I've gotten very chatty at the end of this semester. Like more so. I feel like y'all are trying to like slow things down in the course. That's what you're trying to do.
And we trying to do distractions.
Right. No, I'm okay with this.
We just been
We'll
getting
do what we do.
acquainted.
Huh?
We just been getting acquainted with each other.
Right, right. Okay? Y'all clear on this? You can do this? The vectors, it's really just vectors is all it is. The cross product's sort of new, but like with this stuff, it's knowing your vectors. I think most of you are pretty good at vectors. All right. Let's look at torque on a current loop. This is kind of fun. So if I have a loop of wire that's in a magnetic field, then it will experience a torque if there's a current running through it. And so if I have these sides, A and B, or rather these sides A, where the current's running either parallel or anti-parallel to the magnetic field, what's the force on that? No, they don't cancel out. I mean, they do, but they're zero because they're either parallel or anti-parallel, either 0 or 180, and sine of 0, 180 is 0. So the magnetic forces on those side A, there is no force on those. But then the magnetic force on side B, like if I first consider this force, I have a current or a L that's going in this direction, and then a magnetic field that's in this direction. And so I can figure out what's the direction of the force.
This one's going to be out of the page and the other one's going to be into.
For this one, the force on this one is into the page.
Oh wait, right hand.
Yeah. And the force over here is out of the page. Right, so I get this loop. If it's allowed to rotate about this axis, I have one force pushing in here and one force pulling out. And so it's going to rotate in this direction. Well,
Counterclockwise, right?
it depends how you're looking at it. If you're looking at it from the bottom to the top, but it's just going to rotate in this direction. All right. So,
The left side's all.
On?
hmm?
No.
Yeah, 0 newtons.
I have to figure it out.
I was like, on?
Okay? So the magnetic force on side B, on the left-hand side, it's into the page. On the right-hand side, it's out of the page. All right? Which causes this this rotation. Well, I think I missed
So
it.
nothing's cool with the machine. Cool world.
Oh, I can also calculate this. I'm sorry, that's really what I meant here. I can calculate this force. It's equal to I times the length of the wire, which is B, or I, L, B, sine theta. But L is equal to little b times big B, which is the magnetic field, times the sine of theta, but the sine of theta is just equal to 1. So the force on either one of those sides is I, BB. Little b is the length of the wire, right? And the forces on either side of the loop, like if this is F1 and this is F2, they're equal in magnitude. Same magnetic field, same, magnitude. All right? Down from here. All right, so we can also calculate the torque. By the way, all these equations for torque and stuff, they're all on your equation sheet. You just need to make sure you're familiar with them and that you know what they're referring to and what the variables are. So we can calculate the torque on this. If you recall, torque is equal to the force times the moment arm times the sine of theta. Remember, it was a cross product as well. Actually, to be more correct, it would be R times F sine theta, because remember torque was R cross F. So we can calculate this torque. It's going to be the length of the moment arm, which is A over 2, because we have this loop that's rotating about an axis. Go to the previous page. It's rotating about this axis. My force is applied at this distance, which is a distance A over 2. Right? So it's that length of the moment arm times the force, F1, plus A over 2 times F2. And then I know what F1 and F2 are. They're IBB. This derivation is not terribly important. I just wanted to show you how this torque comes about. And then also, we know that the area of the loop, in general, the area is the side times side, or A times B. So I can calculate my net torque. If I combine these two, I get A, I, B, B. And then if I see that A times B is area, I get this, I times B times the area. All right, so that is the torque. The torque is equal to IBA, where A is the area. Again, that's on your equation sheet, but you just need to be aware of what that is. And this applies to any shape. I mean, this is derived for a rectangular loop, but if it's a circular loop, as it usually is, the area can be pi r squared for a circle. Just because I define this length right here as lowercase b. I did that right here. So yeah, L is equal to b.
So if you were given a problem that said L equals multiply, you would put that in lowercase b.
Right. But the b goes away. Right, like in the final, I mean, it was just sort of a placeholder because in the final equation, that b isn't here, right? Because we convert that into an area. It was really just a derivation to see how we get to that area.
So like it could be any of the letter H, R.
I don't care what it is, yeah. You don't need to know the derivation, but I want you to know how to calculate that torque. All right. And then also, if there are multiple turns of wire, usually it's a capital N, the torque just increases by that number of wires. Let's just sort of make intuitive sense to you. So if you have more than one turn, it's N equal N times I times B times A. All right, we'll talk about electric motors more. I want to go ahead and show you this one, though, because it's kind of cool. A student made this. I think this is called the commutator. This is just a coil of wire. This has multiple turns of wire, and they just put this on there to be, I don't know, cute or whatever, like it actually does something. But
Oh, I thought it should like, I thought they were
it's you can sort of feel a breeze off of it. But anyway, you put a current through this wire, and it sits in a magnetic field. And they took a bunch of magnets to generate a magnetic field. So there's a permanent magnetic field right here. And then you can put the coil of wire in here. It sits on these copper leads. And then there's a battery pack down here. The batteries are getting a little weak because it's a couple years old, but it will generate a current through that wire. Now it's not enough to start on its own. You sort of have to kick start it. But if you turn it, it'll keep going. I'm going to take the leads off. You can see it stop. We'll talk about how electric motors work. There's actually several things that go into this because we'll see next time how when this thing flips over, the force will change direction. Because it's like our current is now going in a different direction than it was previously. But we'll see that next time, and we'll talk more about how these electric motors work. They're actually kind of cool. All right, I think we'll just call it quits there. All right, any questions? Good to go? Have a great day. I'll probably be out this afternoon after about 2 o'clock. I'll send an email out. Yeah, Joseph?
Batteries. This is a random question. Are we going to do